Okay, let me start. Today we're going to talk about the orthogonal set. So before starting, let's recap the last lecture. So in the last lecture, we've talked about the inner product. So if we have the vector u and v in Rn space, so inner product is defined something like this, right? So the each element multiplication with the aggregation for the every element in the vector. So this is the definition of the inner product. So yeah, so this is the definition. So inner product, the inner product have the several properties, something like this. The first one is the uv times uv is equal to vu, right? So and there is the following properties, right? Then this property b and c can be generalized as something like this, right? So the linear combination of the vector u1 through the up with the dot product with w is equal to something like this, right? So this is some property, and we've also talked about the length of the vector, right? So length of the vector v is a non-negative scalar defined by the scalar inner product v and v, right? So it can be defined something like this, right? So in other words, the length of the v is the square root v1 square plus v2 square plus vn square, right? So this is the length of the vector. So yeah, there are some kinds of property of the length of the vector. If we normalize the arbitrary vector with their length, those kinds of vector can be the unit vector, right? So if you remember this figure, if we can normalize any kind of the vector into the circle in 2D space or the sphere in 3D space, right? So this is a unit vector, and right. And what is the distance between the vector u and vector v? So distance vector u and v defines something like this: u minus v, the length of the u minus v, right? So yeah, here was the definition, and then there was one more concept called the orthogonal vectors, right? So if the vector u and v are perpendicular, something like this, these vectors called the orthogonal, right? In other words, the inner product u and v is equal to 0, and two vectors u and v in Rn space are orthogonal to each other. Okay, so this is the orthogonal, right? So this is the another viewpoint of the inner product. So inner product can be defined something like this: u inner product v is equal to length of the u times length of the v times the cosine theta. The theta means the angle between vector u and vector v, right? So if we go back to the orthogonal definition, inner product u and v is equal to length of the u times length of v with cosine theta, right? So 0 means theta is what? 90 degree, right? So it means that the u and v is perpendicular, right? So this case called the orthogonal, right? So these two vectors called the orthogonal, okay? So yeah, it was the last lecture. So today we're going to introduce the orthogonal set. Okay. So by the way, before starting, let's recap the homework 2 notifications. So there was homework 2, right? So the due date will be the May 21. So please start your homework earlier. Okay, let's start today's lecture. A set of vector, a set of vector u1, u2 through the up in Rn space is said to be an orthogonal set. Orthogonal set if each pair of the distinct vectors from the set is orthogonal, that is ui inner product uj is equal to 0. Okay, whenever I is not equal to j. So it means that if any kind of the pair of the vector from the set is orthogonal, this set is called the orthogonal set. Okay, so this is definition. From this one, there is a theorem. If the set S is equal to U1 through the UP, right? If the set S is an orthogonal set of the non-zero vectors in Rn space, then S is linearly independent. Hence, is a basis for the subspace spanned by S. Okay, so the linear independence means this set is the basis for the subspace spanned by S, right? So let's prove this one. Okay, so if 0 is equal to C1 times vector U1 plus CP times vector UP for some scalar C1 through the CP, then we can decompose this equation something like this. So 0 is equal to the 0 vector inner product U1 vector, right? So from here, this one inner product U1 can be decomposed something like this, right? Why? From the last lecture, there was the property of the inner product, right? So if you remember this one, we can easily decompose something like this, right? So from the C1 times U1 inner product U1, C2 times U2 inner product U1, CP times UP inner product U1, something like this, then this term will be 0. Why? Because the U1 and U2 are orthogonal set, so it means that U1 inner product U2 is equal to 0, right? So every another term is also 0, then this term is also 0, right? So finally, this term will be something like this, right? Because the U1 is orthogonal to the U2 through the UP, right? So since the U1 is non-zero, then U1 times U1 inner product U1 is also non-zero, right? Then so from here we can say that C1 is equal to 0. C1 is going to be equal to 0, right? So in other words, similarly, CP through the C2 through the CP must be also 0, right? Similar to this one, right? So in other words, from this equation, C1 through the CP should be all 0, right? So what does it mean? This U1 through the UP is linearly independent, or the set S is linearly independent. Okay, so this is a proof. So in other words, if the set S is orthogonal set, then set S is linearly independent or basis for the subspace spanned by S. Okay, so this is the definition of the orthogonal set. Okay, here's one more theorem, one more definition. An orthogonal basis for the subspace W of the Rn space is a basis for W that is also orthogonal set. So the orthogonal basis means it should be basis for the W and it should be orthogonal set. Okay, so if you remember this theorem, this definition is also very intuitive, right? So do you remember the definition of the basis, right? What was the basis? linearly independent set of the vector, right? So if you don't remember this one, please go back to our lecture 8.3 or 8.2, something like this. Okay, so this is very intuitive definition. Okay, now we have the orthogonal set and orthogonal basis, right? Then we can derive this theorem. Okay, let's the set of the U1 through the UP is the orthogonal basis, right? Orthogonal basis for the subspace W in Rn space. For each Y in W, the weight in the linear combination, because the U1 through the UP is orthogonal basis, so we can represent this vector Y as a linear combination of this orthogonal basis, right? Something like this. Then in here, this weight can be represent something like this. Okay, so for J is equal to 1 through the P. So in other words, if we have the orthogonal basis, and if we have some arbitrary vector Y in W subspace, then we can represent the Y with some arbitrary weight C1 through the CP when CJ is represent something like this. Okay, so let's represent this one. Okay, so let's represent this one. Okay, so let me start from here, right? So the orthogonality of the U1 through the UP shows that Y inner product U1 is equal to this Y inner product U1, right? Then so from similar to here, right? We can derive the C1 times U1 inner product U1 because Uj isn't that no, it's not. U1 inner product Uj is equal to 0 when J is not equal to 1. Okay, because this is definition of the orthogonality, right? Then since U1 inner product U1 is not 0, the equation can be solved for the C1. So from here, by dividing this one on left hand side and right hand side, we can derive the C1 is equal to U1 inner product Y inner product U1 over U1 inner product U1, right? From here, right? And then to find the Cj for the J is equal to 2 through the P, then we can also compute the Y inner product Uj. So we can similarly define the Cj in terms of the Uj, right? Similar to this one, right? So in other words, from here we can compute the Cj is something like Y inner product Uj over Uj inner product Uj. Okay, so this is the theorem to represent the arbitrary vector Y in terms of the orthogonal basis. Okay, so this is very intuitive. One more thing. So what do you want to do? So let's say we have the vector U, something like this, and vector Y, something like this. Then we want to find the projection from Y to vector U. So this projection should be perpendicular. So in this case, what is the Y hat? What is the Y hat? So let me find out the Y hat, right? So intuitively, Y hat is going to be alpha times U. with the arbitrary value alpha, right? So the problem can be reformulated how to find alpha. How to find alpha. Okay? Okay, let's start. So given a non-zero vector u in Rn space here, consider the problem of decomposing a vector y in Rn space into the sum of two vectors, this one and this one, right? One multiple of the u here, and the other orthogonal to u here, right? So we wish to write the vector y to the one multiple of the u and orthogonal to u. So something like this, something like this, and something like this. Okay. Okay. So where y hat is equal to alpha u, right? For the sum scalar alpha, and z is a sum vector orthogonal to u. Okay. So what I want to do is to find out the alpha that satisfies this problem setting. Okay. So given any scalar alpha, let z is equal to y minus alpha u, right? Z is equal to y minus alpha u. Why? This is y, this is alpha, this is the y hat. So y minus y hat should be here. So this vector is equal to this one. So let's say z is equal to y minus alpha u. Then, so that one is satisfied. Okay. Let's suppose this is equation 1. Okay. So that equation 1 is satisfied, then the z is orthogonal to u if and only if y minus alpha u equals z, right? Z inner product u is equal to 0. Why? Because these two vectors are orthogonal or perpendicular to each other, right? So in other words, we can separate this term something like this. So u inner product, y inner product u minus alpha u inner product u, right? So finally, y inner product u minus alpha times u inner product u. Then equation 1 is satisfied with z orthogonal to u if alpha is something like this, right? So from here, we can represent alpha with this one and this one, right? Something like this, right? So alpha is here, then we can represent y hat with the alpha, something like this, okay? Okay, so what does it mean? The y hat can be represented with the y and u. How? Here. So y inner product u over the u inner product u times u. Okay. So in this case, this vector y hat is called the orthogonal projection of the y onto u. So as you can see here, so this y star, this y hat is the orthogonal projection of y onto u. Okay, so this is the definition of the orthogonal projection of y onto u, and the vector z here is called the component of y orthogonal to u. Okay, so component of y orthogonal to u. Okay. So this is the definition of the orthogonal projection. Okay. So in other words, if C is any non-zero vector, non-zero scalar value, and if the vector U is replaced by CU in the definition of the Y hat, then the orthogonal projection Y onto CU is exactly same as the orthogonal projection of the Y onto U. Why? Because where's that? So orthogonal projection of the Y onto CU, orthogonal projection of Y onto Y onto U was here this one, and orthogonal projection of Y onto CU will be what? Will be what? Something like this, right? C, right? So in this case, this value C is the eliminated each other, right? So this term will be so as you can see here, this term is exactly the same to this one, right? So in other words, orthogonal projection of the Y onto U is equal to orthogonal projection of the Y onto CU. Okay, here. So this projection is determined by subspace L spanned by U. So what does it mean? Yeah, let me draw something. So okay, let me draw it like that. So there's no one. Here's that. But yeah, let me draw. So let me say there is the vector U, right? Then the span U, the span by U is equal to line through the U and 0. So this is L span of U, vector U, right? Then let me say there is another vector Y, right? Then we want to find the projection vector Y hat, right? So in this case, the Y hat is denoted by projection Ly. Projection Ly. So it is called the orthogonal projection of the Y onto L. In other words, the Y hat is projection L of Y. So it can be represented Y times U, Y inner product U over U inner product U times U, because this one is exactly the same to this one, right? So this is the definition of the orthogonal projection. Okay, so what does it mean? From here we find a way to find out the projected vector of the on the vector U, right? So in other words, so the orthogonal projection of the Y onto the L is defined something like this. Okay, let me use this theorem to define the another following property. Okay, so before that let's solve this example first. So let's say Y is equal to this one, U is equal to this one. Find the orthogonal projection of the Y onto U. Orthogonal projection of the Y onto U. Then write the Y as the sum of two orthogonal vector. One in the span U. Another one is orthogonal to U. Okay. So first of all, first of all, we have to compute this one, right? So y in the product u is equal to 40. Y 7 times 4 plus 6 times 2, right? So what about this? Vector u, inner product vector u is equal to 20. Okay, so from here, orthogonal projection y onto u is equal to y hat. So y hat is equal to y inner product to u over u inner product to u times u. Okay, so this is the 40, and this is the 20, right? Then here is the u, right? So this is the 2. So this vector u is equal to 42, right? So finally, y hat is equal to 84, right? What about the component of y orthogonal to u? Because this is defined y minus u hat, so 76 minus 84. So this one is equal to -1, 2, right? So if we can draw this one, this is a span u, right? And this is the y minus u hat, and u hat is here, right? So from here, u hat is here, and y minus y hat is here, then y is here, right? Right? So in other words, we can project this vector y onto the line with the vector u to here, right? Then this vector and another this vector can make the y again. In other words, this y is the projection vector on the line of the span u from here. So this one, right? So this one, right? If the calculation above are correct, then y hat with the y minus y hat and y minus y hat will be the orthogonal set. So as you can see here, this one is equal to 0, right? So since line segment between y and y hat is perpendicular to L, so y and y hat is perpendicular to L, because L is here. By construction of the y hat, the point identified the y hat is the closest point of L to y. So as you can see here, there are so many points in on straight line L, right? Then which point is the most close point to the y? Which point is most close point? This one, right? So this point is the closest point to y, right? So this is closest point to y, right? Okay, so this is the concept of the projection between two vectors, right? So yeah, so okay, let's move on. So here's one more definition: the orthonormal set. Actually, previously it was the orthogonal set, right? But here we want to introduce the orthonormal set. So here's the definition: a set y1 through the yp is called the orthonormal set if an orthogonal set of the unit vector. So it means that each vector, these vectors are unit vectors. So So if the W is the subspace spanned by such a set, then U1 through the UP is the orthonormal basis for the W. Since the set is automatically linearly independent by theorem, right? By theorem what? By this theorem, right? Because orthonormal set in, okay, let me draw something. So this is orthogonal set, and in here there is orthonormal set, right? So the simplistic examples of the orthonormal set is the standard basis E1 and E1 through the E1 through the En, right? So E1 is something like 1 0 0 0 0, right? And En is 0 0 0 0 1, like this, right? So this is the one examples of the orthonormal set. Why? EI inner product EJ is equal to 0 when I is not equal to 0, right? And EI inner product EI is equal to 1, right? So this standard basis also normal set, right? So in other words, any non-empty subset of the E1 through the En is also normal. Why? Because they satisfy this one, right? So this is the definition of the also normal set, right? Okay. Let's prove this one. Show that the V1, V2, V3 is equal. V3 is an also normal basis of the R3 space, where the V1 is something like this, V2 is something like this, and V3 is something like this. This is V3, right? Okay, so let's prove this one. So first of all, we have to find the inner product of the each vectors each other, right? So first of all, V1 inner product V2 is equal to something like this, right? Why? This is V1 inner product V2 is equal to this one times this one times this one plus this one times this one, right? So in other words, so from here, this one times this one is equal to this one times this one equal to here, and this one, right? So it will be 0, right? V1 inner product V3 can be similarly estimate something like this from this one, and this one, right? What about V2 inner product V3? So you'll be something like this, right? So from here, we can say that this V1, V2, V3 is an orthogonal set, right? Because they are orthogonal each other, right? And then to show this is also normal set, we have to show each vector has the length 1, or they are unit vector, right? So how can I prove that? Let's compute the V1 inner product V1, right? So V1 inner product V1 is equal to something like this. It should be 1, right? V2 inner product V2 is also equal to 1. V3 inner product V3 is also equal to 1, right? Which shows that V1, V2, V3 are unit vector, right? So from here, because they are orthogonal set and they have a unit vector, right? So V1, V2, V3 is an orthonormal set. Okay, so we proved this one. Since the set is the linearly independent, right? Why linearly independent? Why? From the, where is that? From the definition. Here. orthogonal set if the set S is orthogonal set and S is linearly independent from this proof, right? So in other words, these three vectors form the basis for the R3 space. Basis for the R3 space, right? Something like this. So this V1, V2, V3 form the basis for R3 space, right? Because these three vectors are linearly independent, right? So if you want to check this one, please see our what was that? What was that? There was the theorem to show the relationship between linearly independent set and basis. What was that? What was that? Okay, let's go back to our previous lecture. So what was that? Here. So it was the invertible matrix theorem, right? So it's not our lecture. Where's that? No. Here. Yeah, here. So this is the invertible matrix theorem, right? So actually in previously there was invertible matrix theorem, so but here it's a continue. So in other words, by let me use this. By using invertible matrix theorem, we can say the linearly independent set is form the basis for the R3 space, right? So in other words, the vectors in an orthogonal set of the non-zero vectors are normalized to have the unit vector, unit length, on the new vector will still orthogonal, and hence the new set will be the orthonormal vector. So what does it mean? Let's say there are some arbitrary vector here, here, here. Then if we normalize this arbitrary vector, then we can get a new unit vector, something like this, right? So in this case, these three vectors are orthogonal, and these three unit vectors are also normal, right? So by normalizing the arbitrary set of vector to the unit length, then those projected vector will be the orthonormal set. Okay, so this is the concept of the orthonormal set. Okay, so here's one more theorem. Now this is very important theorem. So actually we will discuss the orthonormal theorem to derive this term. Okay, so which concept will be connected to the eigenvector and eigenvalue or singular value decomposition in the following our lecture. So this is very important theorem, but this is very easy. Okay, let me show you this one. Okay, so on M by N matrix U, M by N matrix U has the orthogonal column. So okay, let's say matrix U looks something like this, right? u1, u2, un, right? Because the size of this matrix is m by n, right? So in this case, the matrix m by n matrix U has orthonormal column if and only if U transpose U is equal to I, identity matrix. Okay, so what was the definition of the orthonormal column? What was the definition of orthonormal set? Okay, what was the definition of the orthonormal set? When ui inner product uj is equal to 0, when I is not equal to 0, and ui inner product ui is equal to 0, right? So this is the definition of the orthogonal set. Okay, so let me prove this one. To simplify the notation, we suppose that U has only 3 columns. Okay, in case each vector in R3 space, right? So let me say that the vector matrix U is equal to vector U1, vector U2, and vector U3, right? Then let's compute the U transpose times U. So what is the U transpose here? And what is the U here? Okay, so let's compute the matrix multiplication between this one and this one, right? How? By the way, this is the one. Let me see. Yeah. First of all, we don't know the dimension of this vector, but let's say this dimension of the vector U is equal to what about, let's say 3, right? So in this case, this matrix is 3 by 3, right? And this matrix is, okay, let me say 4, right? Right? So in this case, this one is 3 by 4, and this one is 4 by 3 matrix. So in this case, this one is same, so we can compute this matrix multiplication, right? So how? This first term is computed by this one and this one. Why? By row column computation, right? So please go back to the matrix operation to compute this one. This is really important, right? But here we can just skip this one. But this one compute this one by this one. This one compute this one by this one. This one compute by this one and this one, right? What about this? This computed this one times this one. This is computed this one times this one. Something like this. Okay. So we want to show this matrix is the identity matrix, right? So what does it mean? This term is equal to 0 and equal to 1, and this remaining term should be 0, right? So the columns of the U are orthogonal if and only if the U1 transpose U2 transpose U1 is equal to 0 here, right? And U1 transpose U3 transpose U1 is equal to 0 from here, right? And U2 transpose U3 is equal to U3 transpose U2 is equal to 0 here. And the columns of U all have the union length if and only if the U1 transpose U1 is equal to 1. Here is equal to 1, right? So the theorem follows immediately from equation 3, 4, 5. Okay. So by definition, if the U transpose U is equal to identity matrix, then the column vectors of the matrix U has the orthogonal column vectors. Okay. So this is the theorem by orthogonal set. Okay, so here's one more property of the orthogonal matrix U with the orthogonal column. Let me say the matrix U is an n by m matrix with the orthogonal column. Then we already know U transpose U is equal to y I, right? From here, from this one, right? Then and let x and y be in Rn space. Then there are three properties. First one is matrix U times vector x. The length of the matrix U times vector x is equal to length of the x. Okay. Let me prove this one first. Why? What was the definition of the length? What was the definition of the length? Here, right? So length v is equal to square v inner product v, right? So length u square u times x is equal to square u transpose x and u no ux transpose with ux, right? Because here this is the inner product, right? So by the property of the property of the transpose, x transpose u x, right? By transpose theorem, transpose property, right? Then u transpose u was what? Identity matrix, right? From this definition, right? So in other words, this is the u x transpose x. So in other words, this is the length of the x. This is the length of u x, like this. So length of the u x is equal to length of the x itself. Okay. Another property is that ux inner product uy is equal to x inner product y. Why? This proof is also intuitive. You can just see here, right? This one and this one and this one, right? So this is true, right? Then from here, ux inner product uy is equal to 0 if and only if x inner product y is equal to 0. So because this property, right? So in other words, what does it mean? Okay, let's say we have the vector x here, and if you remember the linear transformation by matrix U, matrix U, then it will be output of U transpose x, U times x, right? So in other words, the property A and C say that linear mapping from x to ux preserve length and orthogonality. So let me draw something like this. Okay. Let's think about the 3D space. And vector x is here, right? Then there is another space, and vector ux is here, right? From this theorem, length of this one is equal to length of this one. So in the projective space, in the transformed space, the length of this vector is equal to this one, right? From this definition, and from this one, let me say there's one more vector, y, and let me say that there is a projected uy here. Then let's say this vector x and y is orthogonal. Then the transformed space, these two vectors is also orthogonal, right? Because the property of this one, right? So this is a very, very important property of the orthonormal set. Then by using this property, we can derive the eigenvalue decomposition or the singular value decomposition. So let me summarize this one in Korean. 이제 오늘까지 배운 걸로 하면 저희가 이제 이너 프로덕트부터 시작을 해서 올소노멀러티가 무엇인지랑 올소노멀러티가 무엇인지까지 쭉 정리를 해왔습니다. 사실 이제 보면은 오늘 뭐 Theorem도 많이 나오고 어떤 복잡한 얘기들이 계속 나오는데 이제 사실 이걸 보여주기 위해서 저희가 오늘 여기까지 온 거고요. 이제 어떤 우리가 AX equals B를 문제를 풀려고 했을 때 이제 저희가 다양한 방법들을 풀어왔는데 사실 LU 디컴포지션이라는 걸로 이제는 어떤 매트릭스를 L이랑 U로 디컴포즈를 해서 사실 풀었을 때 뭔가 이피션트하게도 풀 수 있고 뭐 다양한 어드밴테이지들이 있었죠. 근데 이제 저희가 더 나아가서 어떤 아비트라리 매트릭스 A를 LU 디컴포지션이 아니라 LU 디컴포지션보다 조금 더 좋은 성질을 가지고 있는 하나의 새로운 디컴포지션 방법을 제안을 하고자 합니다. 아이겐밸류랑 아이겐벡터라는 컨셉이고, 사실 이제 이 아이겐밸류랑 아이겐벡터라는 컨셉은 이제 저희가 컴퓨터 사이언스 필드에서 이제 공부를 시작한 여러분들이 앞으로 계속 보게 될 어떻게 보면 매트릭스 디컴포지션 방법입니다. 그래서 이제 이런 매트릭스 디컴포지션 방법을 딜라이브 하기 위해서는 우리가 이제 올소 노멀이라는 컨셉을 알아야 되고, 지금 오늘 배웠던 이제 올소 노멀 셋이라는 개념으로부터 어떠한 트랜스폼된 스페이스 상에서 우리가 원본 스페이스 상에서 가지고 있었던 랭스나 어떤 올소고널한 특성들이 트랜스폼된 스페이스 상에서는 또 보존이 된다. 즉 어떤 매트릭스 U라는 게 올소노멀 컬럼들을 가지고 있을 때 이러한 성질들이 보존된다라는 특성을 이제 우리가 아이겐밸류 디컴포지션이나 더 나아가서 SVD, 즉 싱귤러 밸류 디컴포지션 같은 방법들에 이제 사용이 되는 것입니다. 그래서 이제 저희가 6장까지 많이 왔고, 이제 더 보면서 남아있는 디컴포지션 방법들이 무엇인지, 즉 우리가 AX equals B를 더 잘 풀 수 있는 방법이 무엇인지를 이제 남은 강의에서 또 배워보도록 하겠습니다. 네, so this is the end of today's lecture. Okay, before finishing, please remember there's homework 2. The due date will be the next week, so please start the homework as soon as possible. Okay, thank you very much.